Hello and welcome everyone to a new episode of our Espresso series. Today we will try to answer a question that tingled mine and Andrea's mind a couple of months ago. And the question is, how can we use WebAssembly to streamline user-defined function development? As I just spoiled, let's say, today we have Andrea Fonti as a guest. Hi, Andrea.
Hello, Antonio. Thanks for having me.
And as usual, you are very unlucky. I'm your host, Antonio. So let's start from the basics. The question is, how can we use WebAssembly to streamline user-defined function development? But what are user-defined functions?
Okay, so like the name suggests, user-defined functions are extensions that are provided by the user to another system. Let's begin with an example, something that lets us contextualize it in the data engineering ecosystem. Let's pick Hive, for example, as a query engine. We have a query engine that lets us perform SQL queries on some kind of dataset. Let's assume that we have maybe some column that has data encoded in a particular binary format. Usually in SQL, we are accustomed to having functions like trimming strings, concatenating strings, parsing date. Let's say we want to supply a user-defined function that lets us deserialize that particular binary format or any other kind of task. Currently, for example, in Hive, we can implement user-defined function in Java, putting those user-defined function in the class path, in Hive's class path, and then register those and make those available via SQL. The same can be done in other kind of SQL runtimes. So, for example, also in Spark, you can declare UDFs and also UDAFs for array handling, and that is the same concept. So we're going to extend a SQL engine providing new functions.
Yeah, and this is also goes back to even old relational databases. I guess most databases are uh, it's possible to extend them, injecting some user-defined function either in SQL, and that's the easy case, or even with libraries and dynamic libraries or compiled libraries that we need to inject inside the database itself. So very similar to Hive example that Andrea just gave us. And the other must do question is, and what is WebAssembly? Where how does WebAssembly can possibly relate to user-defined functions?
Yeah. So let's look at WebAssembly like it was an architecture, a CPU architecture. Now we are accustomed to writing a C program, a Rust program, some kind of program, and then having to compile it to x86 assembly or maybe ARM assembly, ARM machine code. So let's imagine that a virtual architecture exists that no hardware computer implements, but that a runtime system is able to understand and convert to actual machine code. So, for example, a while ago it was popular to compile C programs to JavaScript, for example, via mscripten. That is something similar, but our architecture is not made of simple instructions, but our target architecture is like directly JavaScript codes. code that still needs to be parsed, still needs to be interpreted, etc., etc. But the JavaScript runtime, modern JavaScript runtimes are quite good in optimizing code and generating code that has near native performance. So let's skip the JavaScript layer and let's define a binary format that directly encodes this instruction set for this virtual computer that does not exist. Together with this instruction set, for example, in the x86 land, there are some registers that are not actually registers, but maybe memory mapped peripherals or memory mapped interrupts, something that lets you call system calls, call inside the BIOS some functions that are provided by the machine vendor, something like that. So together with the architecture, there is kind of a runtime of an execution environment. So WebAssembly also defines the execution environment, a flat linear address space that is isolated from the host program, and also some modules, some external functions that we can look at, like those were system calls, something like that. So for example, if in WebAssembly you want to access networking functions, those needs to be provided by the WebAssembly runtime. Then after we define this runtime and this instruction set, we can create a Wasm execution environment and host it in our preferred language. For example, there are a lot of libraries that lets you create WebAssembly hosts in Rust. There are libraries that lets you host WebAssembly code inside a Java virtual machine. And so you can integrate foreign modules written in arbitrary programming languages inside your own runtime.
So this opens a lot of possible new integration and customization over all new kind of platforms. So, for example, a lot of limitation we found nowadays into managed services is that they are not so extensible because, first of all, if it's not an open source project, for example, they would need to give you some kind of API or SDK to develop their function, a function that is compatible with their system. And they would also have the problem of your code potentially doing risky things as if it was the system you are using. For example, if you want to implement a user-defined function in Snowflake, you provide Python code that at some point will execute as Snowflake a Snowflake process itself, and they have to put a lot of guardrails in order to make that secure, because you could potentially try to read someone else data or someone else memory in some way, and that's very risky. WebAssembly gives, by definition, this kind of sandbox where you could bring in a program written by someone else, and through this interface, it's possible to control what this program can do inside your own process and allow for a lot of customization that today is very expensive and very hard to do, to the point that almost no one actually gives you this kind of API, and you rely on deploying other services or deploying yourself the services. So now the next natural question would be, how can we mix these two? What are the possibility that we open up when we start writing user-defined function in Wasm?
Yeah. So First thing that comes up to my mind is you can write arbitrary code. So arbitrary code can be hosted in a shared environment. As you said, this is especially useful in software that is exposed as a service. So, for example, Cloudflare in their Edge offering lets you run Edge functions on their Edge workers. And so is letting you executing arbitrary code into performance critical appliances. So you could hijack the address space of other functions running. You could crash that machine. But having this Wasm runtime lets that service be able to run arbitrary workload by actually sandboxing those and preventing crashes or a hijacking of the address space, for example. But the real value here is letting the user be able to write workloads in the language that is most familiar to them. So, for example, if you want to write a user-defined function for Hive currently, you have to write it in Java. You have to respect the Hive interface, etc., etc. It will not run outside of Hive. You could use Java libraries, but maybe you should take care of being compatible with the class path of the host environment, a lot of stuff. In WebAssembly, you can just develop maybe a simple function in C++ or in Rust. The dumbest example that I can give is a function that increments a number, for example, and that will get compiled down to WebAssembly at near native speed. And you could use so the tool of your trade, the library is typical of your ecosystem, the language typical of your ecosystem. The only requirement is that that ecosystem provides WebAssembly as a target. If you have a language that can build WebAssembly binaries instead of x86 binaries, that system can give you the possibility of writing your user-defined function in that language. And so a lot of integration can happen by reusing code and also not having to learn a new paradigm or new build tools or new execution environments, let me say.
Yeah, that's very interesting. And well, the project that set the initial spark for me and you looking up this kind of stuff was a project named Arrow UDF. So Arrow is a memory format used in data engineering that, well, in the last, let's say, 5 years gained a lot of momentum, and it's used actually to have a common memory format across different uh, execution engine. So how you lay out memory in order to process it is done in a standard way, so that potentially memory can be shared. And I think ROUDF is one of the uh, more neat and I would say impactful, but also easy to understand uh, cases where Arrow makes sense. Okay, I have a memory format, and then I have a way to run arbitrary code but sandboxed thanks to WebAssembly. Now I put the two things together, and that gives us complete freedom about the language we implement the function, the engine that runs the function, and more than everything else, gives us very, very fast execution time, given that the engine natively uses Arrow and doesn't need to convert back and forth. So let's try to wrap this up with a question about weird use cases that you can think about. So, what are the main things that and the weirdest things that can this kind of standards enable for data engineering of the next 5 years, let's say?
Yeah, I think a lot of use cases can be implemented, but the first thing that I want to say is maybe you can write UDFs that are compatible with multiple engines. So, for example, if the calling convention of your UDF is I will pass you an arrow formatted memory buffer with this schema, and you have to provide me an arrow formatted memory buffer with this schema. This could be, in a way, engine independent. So each kind of engine that implements and uses arrow as an interchange format does not need to do serialization and deserialization just to translate the data format in order to call a user-defined function. So, for example, if you develop a user-defined function for Hive, Hive will pass you an Hive-specific data type with an Hive-specific memory layout. So a UDF that you write for Hive is not compatible, even if it was WebAssembly, but without arrow, it would never be compatible with another engine. If we use arrow as an interchange format, we are able to build zero copy architectures since we don't need to copy data only to give it to a user-defined function. And also we don't need to copy data when obtaining results from the user-defined function. But also we could have a lot of reuse between those functions. So improve the overhead in serialization, deserialization. Also, we can do complex code inside the UDFs. So maybe we can look at PostgreSQL. There is PostGIS extension to use georeferenced data. Actually, that extension to Postgre is a C module. So it's something that gets compiled together and loaded as a dynamic library into PostgreSQL. Nothing prevents us to implement the same functionality without extending Postgre in a so invasive way, but as UDFs, since we have libraries maybe in Rust or in C++ or the same libraries that the PostGIS extension uses, we could use those as dependency and re-implement the same surface API, but employing WebAssembly, so never actually building on top of a particular version of Postgre. We have an independent we have independent build cycles. We could reuse the same georeference data function across different engines. So, for example, if our queries depend on some particular function, we can have exactly the same behavior for that function inside the different engines, even if those engines are developed using different programming languages. Our lingua franca would be Apache Arrow and WebAssembly. Another thing we can do is having a complete engine, for example, Data Fusion or DuckDB, built to WebAssembly, and then you can embed the entire engine inside another engine or another application. So, for example, we could use DuckDB that has a WebAssembly target and embed it maybe in a Postgre function. I don't know why you want to do that, but it is doable. Or we could use DuckDB and run it inside the browser. Or maybe augment some functionalities of another engine by embedding inside that engine another engine It could, for example, maybe we have a Flink job with some state. We want to perform SQL queries on that state. Let's provide that state to a DuckDB instance that is running in memory and implemented in WebAssembly, since DuckDB is not Java, so you cannot embed that directly. You could by loading native extensions. Here we are not loading native extensions, but hosting a WebAssembly runtime that lets us execute DuckDB inside Flink, for example. So we have a lot of even stranger use cases than this. A lot of flexibility, and also a lot of WebAssembly runtimes are currently emerging in the software ecosystem.
Yeah, so I think also one interesting use case would be on privacy. The fact that you could take this WebAssembly UDF, execute potentially wherever you want, means you don't need to send data across the network. Sometimes you could even execute them locally on a browser if you want to. Well, it's not just a UDF in that case, but still, I think showcases the potential of these two together, having also a format that enables all these different computation. So I think, as usual, when we are talking about nerd stuff, we end up recording a too long episode, but it was a lot of fun. So thank you very much, Andrea, and see you at the next episode.
Thank you, Antonio. Bye.